Okay, so up to now I've been talking all about hydrocarbons, okay? And the last part, really, I'll be talking about some interesting features of biofuel combustion, okay? So we're looking for new sources of energy, okay? So all sorts, wind power, solar radiation, geothermal, wave, nuclear power, fusion reactors. Any others? Probably. Okay, but combustion is still going to be a big contributor. Okay, certainly in the near term. Okay, so combustion is responsible for most of the power generation in the world. Okay, and Professor Law was saying, what's that? Combustion in the service of humanity. And I actually had a very interesting. I was invited to give a talk last October in the Netherlands. And there was one there about food and cooking and how cooking food has affected our lives. And just being able to cook food means that we can eat a lot more, grow taller, has affected mankind. I can't remember all the details, but even that. So like we're sitting here in an air-conditioned room with all this electricity and lights, and the level of living, you understand what I'm trying to say. The quality of life that we have is really due to cheap energy and the energy that we're using. Okay, so 85% of EU power production comes from combustion, and about more than 90% is of transportation comes from combustion. And perhaps 100 years of fossil fuel remaining. Alternative energy sources are not very mature, and it'll take some time to get those alternatives in place, this infrastructure in place, and so on. So the challenge to us is to limit the adverse effects of fossil fuel use and buy time for alternative energy. Okay. So one possible source will be bio-derived fuels. Okay, so some petroleum will be available. You've got the oil sands and oil shale in Canada. So, and then we've got coal to liquid and Fischer-Tropsch fuels. We have natural gas, hydrogen via electrolysis, so e-fuels really, and bio-derived fuels, so ethanol, butanol, algae, and biodiesel from vegetable oil and animal oils. Okay, and we need to understand all of these alternatives if we're going to use them in combustors. So we need to understand all the complex behavior, ignition, NTC, cool flame, whether a fuel is suitable for use in a diesel engine or a gasoline engine, whatever, right? And also then the product and pollutant formation. So sometimes the product and pollutants might be even higher for bio-derived fuels than there would be for a hydrocarbon, okay, depending on the dioxins and so on, for instance. Okay, and this is just a graph showing some synthetic fuels that can be derived from Fischer-Tropsch processes. Okay, so you have syntrolium, Sasol, IPK, you've Shell gas to liquid, Sasol Oryx, and Sasol Oryx with the isomerized. Okay, and you can see the blue bars here are isoparaffins, and the orange bars are N-paraffins. So you can see here, centered around C10, C12, but in the C8 to C16 region, we have this syntrolium, synthetic petroleum. Okay, and this will be another synthetic petroleum. Okay, and then this will be more a synthetic, well, it's gasoline to liquid, still a gasoline. This one would definitely be more, well, more towards a diesel. Okay, so you can have, depending on the strain and the composition of the fuel, you can have it more diesel-like or gasoline-like. Okay, and with a different composition of N-paraffins as opposed to isoparaffins. Having high concentrations of isoparaffins will make it less reactive and have a higher research octane number and therefore more resistant to autoignition. So Oxygenated fuels are being considered as being cleaner burning. They're considered carbon neutral, but they're not really, okay? So if we take a change in emissions, there's some evidence that particulate matter can decrease by about 50%, CO, hydrocarbons, but NOx can also increase. And this is from a report from 2002. But there's been a lot of controversy over the years, the food versus fuel debate, whether first generation biofuels should be used or not. And in general, it's considered it shouldn't, okay? So, but what about second and third generation? So you use the stalks, you harvest the lignin and so on from that, from wood, convert those sugars into fuels, okay? And the idea is to use the waste matter from biofuel production to generate biofuels, okay? But they do have some advantages. And this is just showing you percentage of fuel carbon converted to sub-precursors on the y-axis versus the fraction of oxygen in the fuel by mass on the x-axis. And you can see that the percentage of fuel in the carbon that's converted to soot decreases with increase in oxygen content in the fuel. Okay, so that's a good thing. Okay, this was actually first published by Miyamoto et al. In a paper at SAE in 1998, and Charlie, I was co-author on this paper in 2006. We published this figure. Okay, essentially, when you get to here, you have 100% fuel. So this point here is 100% dimethoxymethane in the fuel. But so dimethoxymethane doesn't produce soot precursors. Why does it not produce soot? Because there's no carbon-carbon bonds, okay? I didn't go into it, and I don't talk about soot formation, but to get soot formation, you've got the famous Wong-Frenklock mechanism, the HACA, hydrogen abstraction, carbon addition, is that right? Mechanism. And the stem really, it stems from ethylene and acetylene chemistry. Okay, largely. Okay, so there would be C2, carbon-carbon bond. You've got double or triple bonds, and that can lead to polyaromatic hydrocarbons. There's other involvement as well, propargyl, allyl, cyclopentadienyl, and all this chemistry. I won't go into it. There's a rich body of work out there on it. Okay, but you can see that if you have an oxygenate molecule in the fuel, it can decrease the amount of soot because it lowers the number of carbon-carbon bonds in the molecule. So what kind of oxygenated fuels do we have? We have alcohols. So examples are methanol, ethanol, propanol, butanol that we've looked at in the community. Ethers, so dimethyl ether, diethyl ether, ethyl methyl ether, methyl terbutyl ether, ethyl terbutyl ether, lots of different ethers, right? So alcohols, ethers, esters, ketones, and furans, okay? And so these are all oxygenated functionals, okay? So what is the effect of that functional on a reactivity of a fuel? So I'm going to talk about that in the next few slides. So here's a comparison of the reactivity of N-propanol here and isopropanol. Same concentration, same condition. So 0.5% fuel, 2.25% oxygen, phi is equal to 1 at a pressure of 1 atmosphere. Okay, and you can see at the same temperature across the range that N-propanol is about twice as reactive as isopropanol. Or conversely, isopropanol is 2 times slower in comparison to N-propanol. Why? Why is that the case? So if we look at a flux analysis of the reaction. So again, people were asking me about how to do the flux analysis. I'm showing it here. We have a 0.5% fuel, equivalence ratio of 1 at a temperature of 1600 Kelvin. We're looking at the chemistry of fuel consumption at 30% fuel consumed. Okay, so 13% of the fuel is gone. What's happening to the fuel at that edit in the code? Okay, for N-propanol, we see that about 30% undergoes a molecular elimination reaction given propene plus water. But at the same condition, we have 60% of isopropanol undergoing the same reaction. Okay? So it's 30% for M-propanol, but 60% for isopropanol. Okay? So, and here we see the sensitivity analysis. Again, people are asking me about this. How do we define it? Here's the definition here. I didn't include it in slides earlier in the week. Okay? But don't worry. It's just however we define the ignition delay time, the bar is telling you whether it's important or not. A big bar is important, a small bar it's not. Okay? Or it's less, anyway. Okay? So the most important reaction, promoting reaction, is H plus O2. And this bar has been divided by 2. Okay? The next most important promoting reaction is cleavage of a methyl radical, giving you methyl radical plus secondary ethanol. Okay? So this is the carbon atom, a radical site on the carbon atom next to the OH functional group, SC2H4OH. So it's CH3, CHOH radical. Okay? But that promotes reactivity. But the most important reaction, inhibiting reactivity, is the unimolecular decomposition giving propene plus water. This will compete with the decomposition giving us 2 radicals, forming 2 stable molecules. Okay? So here we're getting stable species, here we're getting radical species. This promotes reactivity, this inhibits reactivity. All makes sense. Okay? But we have twice as much of this going on in isobutanol compared to isopropanol compared to M-propanol. So therefore, it's M-propanol is twice as reactive in comparison to isopropanol. Okay? Or isopropanol has half the reactivity compared to M-propanol. You see the same again for M-propanol. This reaction is the most important reaction inhibiting reactivity. The most important reaction promoting reactivity is cleavage giving you ethyl plus hydroxymethylene radical. Okay? Again, 2 radicals promotes reactivity, 2 stable molecules inhibits reactivity. Okay, so how is this reaction occurring? Okay, this reaction occurs through a 4-centered elimination reaction. We have N-propanol, okay, and the hydrogen on this carbon atom, okay, can form a 4-centered transition state ring, okay, 1, 2, 3, 4, okay, so you can have a half bond here, and eventually forming propene and water. I hope you can see that, okay? That's for M-propanol. And the Ray constants here were estimated based on a paper from Wing Zhang, published in IJCK in 1976. Here's the Ray constant. So we have a frequency factor of 3.5 times 10 to the 13 with an activation energy of 67 kilocalories per mole. Okay. Again, if we are going to break the carbon-carbon bond here, what's that activation energy? So what's 368 divided by 4.184? It's about 88, something like that. In the 80s, 85 to 88 kilocalories per mole. Okay, so to break a CC bond, it's about an activation energy of 88. But now here we have an activation energy of 67 for this transition state ring. It's still high, it's not 43, right? But it's a lot lower than 88. Okay, and hence this is going to dominate over the CC bond cleavage. Okay, and hence we see a lot of flux of alcohols giving this molecular elimination reaction given the olefin plus water. Okay, through that 4-centered elimination. And all alcohols are going to do it. So you can consider this as, we'd say, RCOH. Okay, and it doesn't matter what the R is. As long as you have a hydrogen atom there, you're going to get molecular elimination with a similar Ray constant. Okay? So all alcohols are going to have this type of reaction occur. Okay? And here, isopropanol, though here, again, we have 1, 2, 3, 4 centered elimination. We form propene and water. But now look at the frequency factors, about 7 times that, okay? And this is tuned, okay? So but based on degeneracy, what should it be? So here, for N-propanol, we've got 2 equivalent hydrogen atoms, right? And so there's 1 of 2 will form the complex. But here, for isopropanol, we have 3 and 3, 6 equivalent. So this frequency factor should be at least 3 times faster. So a first estimate would be about 10 to the 14. Okay? 3 times 3.5. Okay? So it should be, a first estimate would be 10 to the 14. So I tuned this to fit the data that we simulated, and I multiplied it by a factor of 2. Okay? That's not unreasonable with the uncertainty for this reaction, to increase it by a factor of 2. Okay? And here's the activation energy, exact same activation energy, because it's a very similar transition state. Okay? And they're the rate constants that we did it. Just to say, and this is a little bit of look at me, okay? But Josh Hine published this paper, and I was actually a co-author on this with others. And Josh Hine worked here with Professor Dreyer on the flow reactor, okay, at Princeton. And he measured the rate constant for this reaction, right? And here's his measurement. So these solid points are the corrected rate constants, corrected measurements. Okay, this is the rate constant that was derived. Okay, and again, it is, what I'm trying to say here is that, look, the evidence is the evidence of the experimental data. And sometimes, okay, you estimate the rate constant and you're close to it. And then you have to optimize to get the line to go through the points. Okay, so here, okay, I don't show it, okay? But the model that we had to fit through these points here and through the points here. And the rate constant that I had to use for the molecular elimination reaction, the rate constants that I had to use were these 2. Okay? To get best agreement with the experimental data. And so, but here's a direct measurement of the rate constant, the solid line. Here's a derived rate constant from fitting the ignition delay time from the ignition delay times that we measured in the shock tube. Okay? But you see actually that they agreed quite well with one another. Okay? It's not always the case and so on, but there is when there's constraints on other rate constants. So it's showing you that actually the importance of that molecular elimination reaction in the shock tube experiments, and how even those shock tube experiments, we could get a constrained indirect rate constant measurement of that rate constant. Okay? And this is then, Bowie et al. Did an ab initio calculation, and this was the rate constant that they published. Okay? And I don't have that, but a reference to this rate constant would be in this paper, if you get it. Okay? Now, so that's alcohols. So at high temperature, all alcohols will go through that molecular elimination reaction, giving an olefin plus water. Okay? And that will dominate. So that's something that's different from the alkanes that we spoke about in the last number of days. Okay. So what about ethers? Ethers are alcohols, except the hydrogen has been replaced by a functional group, a carbon atom on the other side. So you replace the hydrogen with a carbon atom, and you have an ether. Okay? So actually, the chemistry may be very similar, and it is. Right? So again, this is at high temperature. Now, this is a very interesting paper, work from Kenji Yasunaga. He worked at the Ministry of Defense in Japan, published in 2011 in Combustion and Flame. And what he did was he took baseline experiments. So we have 1% hydrogen and 1% oxygen and argon at different, so he had a constant initial pressure, okay, and then a range of reflected shock pressures ranging from 1.4 to 2.6, okay. And here are the experiment results that he measured for that mixture. And then he took a series of mixtures, okay, where he replaced just 10% of the hydrogen with an ether, and actually isobutene also, okay. So here's this same mixture now, okay, so these open circles here, and you still have 0.9% hydrogen, but 0.1% of the fuel is isobutene. And or then these red symbols are MTBE, or these open squares are 0.1% ETBE, ethyl terbutyl ether. And you can see that that has a profound effect on the ignition delay time measurement. Okay? Just 10% of the fuel is replaced by either isobutene, MTBE, or ETBE. And there's a big decrease in reactivity. Right? So the ignition delay time shifts from this curve here to this curve here. But they're all very similar. Okay? And it has the same effect virtually. Okay? And then here's the other two. So again, it's the same thing. 10% of the fuel is replaced with diethyl ether and ethyl methyl ether, but the reactivity isn't decreased nearly as much at lower temperature and actually is enhanced at higher temperature. So what's going on there? Okay. So if we look at the ethers, we have the same reaction. So the ether here, a methyl terbutyl ether. So we have a methyl group instead of a hydrogen atom as we had in alcohol. Okay? But we can still have this four-centered elimination reaction. 1, 2, 3, 4. And then we eliminate producing methanol, okay, CH3OH, plus isobutene. Okay? And here's the rate constant for a reaction. So again, the frequency factor is similar in this case to that we had for isopropanol earlier. Okay? Similar. We have 9 equivalent hydrogen atoms instead of 6. Okay? Similar rate constant, frequency factor. The activation energy is lower now. Okay? So it's lower by about 6 or 7 kilocalories per mole. Same ballpark, but lower. Okay? And these rate constants were calculated at this level of theory. Okay? And also then, for ethyl terbutyl ether, so you still have the terbutyl group here, so the same frequency exactly, and pretty much the same activation energy within 0.2 of a kilocalorie per mole. So it's the same rate constant. Okay? So the functional group here really doesn't matter. If you've got methyl, ethyl, propyl, butyl, isobutyl, terbutyl, anything, it doesn't matter. The rate constant is going to be very similar. Okay? But look what's being formed. You're getting isobutene and methanol in this case, isobutene and ethanol in this case. So these terbutyl ethers will also always give you isobutene. Okay? The methyl one will give you methanol, the ethyl one will give you ethanol. Okay? And hence, if we go back here, the effect of adding isobutene to the fuel or adding MTBE or ETBE to the fuel is the same. Because MTBE and ETBE undergo that molecular elimination reaction, producing isobutene and ethanol, or methanol or ethanol. Okay? But in both cases, you get isobutene. And that isobutene is inhibiting the reactivity. Okay? And they're all the same. Okay? What about diethyl ether and ethyl methyl ether? Okay? So if we go back to ethyl, so I had, this is ethyl terbutyl ether. You also can swing this hydrogen around and have a four-centered elimination reaction on this side, if you look at ethyl terbutyl ether. So this is what I've done here. So now we have a 1, 2, 3, 4-centered elimination again. And now we can get terbutanol and ethylene. Okay? But the frequency factor here is a little bit lower than it is if we do it on the terbutyl side. Just on a degeneracy basis, it should be lower. Okay? So it's about a third of the terbutyl, because we have one methyl on this side. Here we have, so we've got 3 equivalent hydrogen atoms. Here we have 9 equivalent hydrogen atoms here. So the degeneracy should be, this should be about 3 times lower, which it is. Okay? And then the activation energy is a little bit higher. So instead of being 60.5 or 60.6, 60.8, 63.4. So this is going to be lower. The rate of this reaction is going to be lower than the elimination giving you isobutene plus ethanol. Okay? You might get some percentage, but not as much. So ETBE will mostly give you isobutene and ethanol, and a little bit of terbutanol and ethylene. Okay? And that's significant, and I'm going to tell you why now in a minute. Okay? Because we move to ethyl methyl ether and diethyl ether. Okay? And both of these have a four-centered elimination again, but they give you ethylene and methanol in the case of EME, and ethylene and ethanol in the case of DEE. Okay? So in these cases, you're getting ethylene and the alcohol, and they have a very similar rate constant. Again, you see, look, the activation energy is higher. Okay? Similar to here, and the frequency factor is similar. Again, the energies were calculated at this level of theory. Okay? So, but you can see now, if we distinguish the ethers, so these ethers, MTBE and ETBE, produce isobutene, so they're all lying here. And you can see ETBE does appear, at least at one point, that's a little bit faster, okay? But it's a little bit faster. You couldn't really argue it. They're all about the same, okay? But diethyl ether and ethyl methyl ether, you can see are, okay, it's slower, but significantly faster than if you produce isobutene. So there's a difference if you produce ethylene. And it actually becomes even faster than hydrogen on its own at higher temperatures. So ethylene is very, very fast to ignite, is what it's saying. Because once you produce it, it will give you high reactivity. Okay? So I asked my postdoc just to calculate this. This is based on our current mechanisms for the fuels. And this is just looking at 1 atmosphere, fuel in air. Okay? So you have about 20% oxygen in each case. Okay? So the oxygen is staying constant. So what's happening, or what's the difference in reactivity? You can see here, ethylene is way faster than anything else. Okay? Here's the predicted reactivity. Okay? So we have isobutene and propene are the slowest. Okay? Why are isobutene and propene the slowest? Here's the radical from propene, resonantly stabilized. Okay? What about isobutene? Same. You abstract a hydrogen atom, you get methyl allyl radical. It's resonantly stabilized. Okay? So in both of those cases, you get a resonantly stabilized radical, which will be hard to oxidize. And so they're going to be relatively slow to react. Okay? So for the case of isobutene and propene, they're the slowest to react. Ethylene is the fastest. And here's ethane. It's fast, but it's not nearly as fast as ethylene. Okay? And why is ethylene so fast? Because when we, and I showed you this earlier in the week, maybe yesterday or the day before, we have ethylene, we get vinyl radical. Vinyl reacts with O2, and we have CH2CHO plus O at higher temperatures. We get formaldehyde plus HCO at lower temperatures, and you get some stabilization at high pressures and low temperatures. Okay? But this is a chain branching reaction because we have one radical giving us two radicals. Okay? So actually, vinyl plus O2 chemistry is very important, and having accurate kinetics for that. So when I was asking Stephen Klippenstein for many years to study that and to produce quite an accurate, he said it's very difficult to study because you've got tunneling, and it's a very difficult system to study using ab initio calculations, quantum chemistry. But it was finally published in 2015. And that was a big improvement for the community, having accurate kinetics for that reaction. Okay? And it results in this very high reactivity for ethylene. Okay? So what I'm saying is, for these reactions, for alcohols and ethers, we can produce, we undergo these molecular elimination reactions. And essentially the fuel, it decomposes so quickly that you could consider the fuel to be like the olefin and the alcohol rather than the ether at high temperatures in that regime. Or the alcohol to be like the olefin and water. Okay? Because it mostly becomes that first and then they go on to react. Okay? So it's the fate of those other species. And then you can see the other species here in between. Okay? So this is going back, again, a similar trend in reactivity as, so what I'm trying to say is, look, this isn't new. Okay? This was published by Alex Burkhardt back in 1971. Okay? So, but it's just to consider what is. I said I'd show you this as well. So this is hot off the press. It's not published, but it's something that I've had my group put together in the last few months. Okay? And we're just showing, here we have fuel in air, phi 1, 30 atmospheres. And we've taken ignition delay data for different fuels. And you can see here's ethylene. Okay? We don't have low temperature chemistry or data yet for it. Here's propene. Here's isobutene. Okay? And then here's 1-butene. Where are we? These black squares. 1-butene, 1-pentene, 1-hexene, 1-heptene. Okay? So if we just look at high temperature, ignore all the low temperature. Let's just take, we'd say from here, this small part of the profile. You see, look, isobutene and propene have about the same reactivity. And they're way slower in comparison to all the others. So here we have ethylene, and then we have 1-butene, 1-pentene, 1-hexene, 1-heptene, 1-octene, 1-nonene, 1-decene. You get the message. We're stuck here. So all of these guys are actually behaving like ethylene. Okay? So you have ethylene, and so this reactivity is controlling everything. It's all coming from that vinyl plus O2. Okay? So all of these other molecules, they're going to produce ethylene in their oxidation. And so it's that vinyl plus O2 chemistry that's controlling everything. Okay? But propene and isobutene don't produce ethylene in this condition. And they produce resonantly stabilized radicals. They're slower to react, and hence the reactivity is much lower. And they're outliers. Okay? But all the others aren't. Okay? If you look then at low temperature, what you see is what you'd expect to see. As you go longer in chain length, the reactivity increases. Okay? As I spoke about. Okay? So that's, I just think this is a nice, why it's related to biofuels, not really, but I just thought I'd bring it in, having spoken about ethylene and isobutene and the differences. Okay? It's just nice to show you. Okay, so we haven't published this. I mentioned this already. I have it here again. I just reiterated that for the oxygenated species, this is dimethyl ether. It's an ether. But the chemistry is essentially the same as for an alkane. Right? And I'm not going to go through it all detail again. I did this already today. So all the chemistry here, there's nothing different from what we would do for an alkane. You have the alkyl radical, isomerization, addition to O2, isomerization, second addition to O2, second isomerization, branching. Okay, same. Okay, and you see similar negative temperature coefficient behavior for dimethyl ether. Okay, as you would in an alkane. Okay. So what about alcohols then at low temperature? Okay. So we know alcohols at high temperature, I've just shown you, will undergo that elimination reaction, giving you an olefin plus water. Okay? What about at low temperature? So so isopentanol is being considered as a promising next generation biofuel, or at least was. Here's its structure. Okay? So there's efficient production routes from biomass exist. Okay? But it also has favorable characteristics as a homogeneous charge compression ignition fuel. So here's gasoline. We have heat release rate over crank angle degree. Okay? So the heat release rate of gasoline is this dotted line. And you can see the heat release rate of isopentanol maps that of gasoline. Okay? That of ethanol actually doesn't. Okay? So it would be a better alcohol compared to ethanol to use in gasoline. Okay? And also, the heat release rate is really showing you the function of reactivity, and homogeneous charge compression ignition engines depend very much on autoignition characteristics. Okay? So if the autoignition characteristics of the isopentanol is close to gasoline, it's better than ethanol. Okay. So what happens then at low temperature chemistry? This slide is actually courtesy of, I can't think of the guy's first name. I can see his face, but I can't think of his first name. Anyway, it's a courtesy of his work from this presentation in 2011. Oliver, sorry, is his first name. Oliver Wells. Okay. And here are then, so we actually looked at it again. Unfortunately, again, it's more ignition delay times, okay? But we looked at, so here's isopentanol oxidation at 5.5, 5.1, 5.2, okay? These are rapid compression machine data taken in Professor Jackie Sung's lab in University of Connecticut, some here and here again. And we took some data actually in Galway. So you can see that here the data agree with one another. There's other data he published here, or plotted here. But you can see that here are high temperature data taken shock tube, and these are low temperature data taken the RCM. You don't see nearly as much NTC behavior. That's one thing that pops out, right? You don't have that strong negative temperature coefficient behavior that you would normally see in an alkane. Okay? There's a little bit of a bump, okay, a turn, but there isn't nearly as much going on as you would see in an alkane. Okay? So the chemistry is different. Okay? So what's going on? Okay? To explain what's going on, let's consider first what happens if you had isopentane. Okay? So here's isopentane plus OH. We abstract a hydrogen atom. Let's just say secondary one for a minute. And we get water and this radical. That adds to molecular oxygen. We get this alkyl peroxy radical. And then we have a 1, 2, 3, 4, 5, 6 member transition state ring. Facile one, we produce this radical. And that radical can undergo beta scission given an aldehyde plus ethylene plus OH. Okay? But what will it do at low temperature, actually? Will it do that? What is the activation energy for this process? So we break this CC bond. Okay? That activation energy is actually about 30 kilocalories per mole, or 34. So it's not competitive, actually, with, and we don't normally see sensitivity to these beta fission reactions. So what gives us negative temperature coefficient behavior? Did I say? From yesterday. Yeah. At the QOH. So at this stage, this is our QOH, hydroperoxy alkyl radical. This is our alkyl peroxy radical, hydroperoxy alkyl radical, right? So we arrive here, and then this can add to molecular oxygen, or it can give us other products, okay? So what do 5-membered rings give us? Typically, olefins plus HO2. What do 6-membered rings do? They go on to chain branching, typically. What do 7-membered rings do? Propagation, yeah. What do they give us, though? Can you remember? Cyclic ether plus OH. Okay? So try and bear that in mind. So here we have a 6-membered ring. I'm including this for a reason. It's a propagation, but it's not going to propagate mostly. Okay? The activation energy is high for that propagation. So under most conditions at low temperatures, what it's going to do is go to branching. Okay? So we can add, this radical adds to molecular oxygen, and we go to branching. Okay, so now let's consider a similar situation for, I didn't take the same one, unfortunately, but anyway, similar situation for isopropanol. Okay, now the most easily abstracted hydrogen atom is on the carbon next to the functional group. So we form that radical. Okay, and that adds to molecular oxygen at low temperature, and we get the peroxy alcoholic radical. Okay, and now we have a 1, 2, 3, 4, 5-membered transition state ring. Okay, isomerizing, to give us this moiety here. And that will decompose to give us the aldehyde plus HO2. Okay? I think I showed this yesterday from the De Silva and Boselli route. It doesn't occur like this. This is activated, and it goes directly from here to here with an activation energy of about 11.2 or 11.4 kilocalories per mole. I showed you that yesterday. Okay? All right. So we have this again. I focused on it. Or we can, if we do the corresponding one, okay? So this one with a very low activation energy goes here. Okay? We had that. It's about 11.4 kilocalories per mole. Right? But say we abstract a hydrogen atom here on this molecule. Okay? We add to molecular oxygen, we get this species. And now we have a 6-membered ring. 1, 2, 3, 4, 5, 6. Okay? That 6-membered ring can also form this radical, giving us this aldehyde plus formaldehyde plus OH. Okay? With an activation energy barrier calculated CBS-QB3 level of 22.4 kilocalories per mole. Now, if we look at it here, so that's on the alcohol side. Okay? And we have one H atom. But we could have also a similar, if we think about it, a hydrogen atom here, right? 1, 2, 3, 4, 5, 6-membered ring on that side. So I have it on the next slide. So there's that one I've just shown you again. But if we do on the other side, 1, 2, 3, 4, 5, 6-membered ring with an activation energy this time of 24.4, calculated at the same level of theory we get this radical. Now, so this radical can add to molecular oxygen. Okay? But what about this radical here? So is this radical going to add with a radical site on the oxygen atom? Is that going to add to O2 to give you chain branching? Are you going to get OOO? Okay? So the O atom is not going to be attracted to molecular oxygen. They're going to repel one another. So there's no way that this is ever going to add to O2. Okay? You're not going to get branching. You're always going to get propagation here. If I go back here, is this ever going to add to O2? Okay? Well, it doesn't occur, actually. It goes, well, anyway. This is never going to add either. So you're always going to get, sorry, it's the previous one I was talking about, this one. So you're always going to get this aldehyde plus HO2. You're never going to get branching. Okay? So once you form this, you're going to go through a concerted elimination reaction, giving you the aldehyde plus HO2. Okay? Once you form this, you're always going to get the aldehyde plus formaldehyde plus OH. It's not going to go on to chain branching. Okay? And so when you have the functional group on an alcohol, you get abstraction even not only at the one next to the carbon atom, but on other ones too, which lead, and you can see the argument here is, okay, I've abstracted, okay, so if I abstract a hydrogen atom here, it's not going to go to branching, it's a propagation. But I abstract a hydrogen atom here, which is not next to it, it's the next one over. Some of it, okay, here the activation energy is 22.2. Here the activation energy is 22.4. This is 2.2 kilocalories per mole lower, forming this species, which can't go to branching. And at low temperature, this is going to dominate over this guy. This can go to branching. Okay? So this guy hanging off, but this can add to molecular oxygen and go on to branching. But it's it's higher in activation energy and therefore lower in rate compared to this at low temperature. Okay? And so for these reasons, alcohols are slower to react relative to alkanes at low temperature because you get a lot more propagation compared to branching, just because you can't get branching from the products that are formed through the species. But again, we're mapping out the chemistry. It's not anything new, right? You still get the alkyl radical. The alkyl radical still adds to molecular oxygen. You still have this internal hydrogen atom isomerization, but the products of those lead to propagations, not branching. Okay? And the chemistry isn't all that different from an alkane, right? Okay, so that's alcohols. So what about esters? Okay, so we've done alcohols at high temperature. We've done ethers at high temperature and low temperature. I showed dimethyl ether. So what about these methyl esters? So this is just showing ethyl tetradecanoate. And this would be a more realistic ester that would be used as a biodiesel. Okay? But all these esters have this functional group where you have this ester functional group. Here we have, methyl butanoate. Here we have ethyl propanoate. Okay? And both of them have C5H10O2 molecular structure. Okay? Again, unfortunately, well, these are two fuels that my group studied. And I know most about these, so I'll talk about these. Okay? So, and it turned out to be a nice study because we have a different molecular structure with the same molecular formula. All right? C5H10O2. Okay. One is a methyl ester. And again, we did this comparative study. Okay? So we took both fuels at the same condition. 1 atmosphere, 4 atmospheres. This is fuel stoichiometric. This is fuel lean. And you can see at all conditions, ethyl propanoate is twice as fast compared to methyl butanoate. Okay? Well, Not all conditions. Here, there's a little bit different, but it's mostly just this one point. It should really be slower. But you can see that it's always faster. Okay, so if we look again at 1% fuel, so here's our condition, 1% fuel, 6.5%. So this is stoichiometric, 1600 Kelvin. We're at 1 atmosphere, and we're looking at when 50% of the fuel is consumed. What's happening? Okay, so methyl butanoate is undergoing unimolecular decomposition and H-atom abstraction reactions forming different radicals, okay, at this condition. Okay, but if we look at the same condition for ethyl propanoate, okay, so we have exactly the same condition, okay, all of ethyl propanoate is undergoing this 6-centered elimination reaction, okay, so we have this transition state leading to the formation of propanoic acid and ethylene. And that's going to happen for all ethyl esters. Okay? So here we have ethyl propanoate. Ethyl propanoate gives us ethylene plus propanoic acid. Okay? Any other ethyl ester, ethyl butanoate, ethyl pentanoate, all the way up, is going to give you ethylene and the corresponding acid. It's probably quite, like here, a lot of the chemistry has developed already. As a rule of thumb, I ask my group, look at when sometime between 10 and 20% of the fuel is consumed, and what's controlling the chemistry then. Okay? If you and this is something I'd share with you, you hear people talking about this. It's an important point. So maybe try and just pay attention to what I'm saying, okay? If we have fuel in air, right, that's quite a concentrated mixture of fuel, right? And so it doesn't matter what diagnostic we use to measure the ignition delay time. So what you'll see is you'll have, if you have an ideal shock tube experiment, for instance, you'll have a very flat pressure profile, and then a very rapid rise in ignition delay time, okay? And I've shown you profiles like that in your notes, okay? That's fuel in air. And so your fuel is disappearing at a very rapid rate. So if you can take someplace between 10 and 20% fuel consumed there, you can see what's controlling all of the consumption, the reactions, all of the consumption of the fuel. Not quite the initiation, but it'll tell you where most of the action is, okay? If you're in dilute conditions, it's very hard, the pressure doesn't rise. So say you have 1% fuel and 4% oxygen. You have 95% typically argon, diluent, okay? Or nitrogen, but mostly argon. If you have 1% fuel, you have very little heat in the system, or potential heat in the system. And so your pressure rise due to ignition is going to be very, very small. So typically, to measure ignition delay times accurately, under those conditions, we use light emission profiles rather than pressure rise. And there it's much more difficult to see things evolve in time, okay? But what I'm trying to say here, there was no ambiguity under this condition. You know, you can, and even under dilute conditions here, the chemistry in the code doesn't know that it's very, you know, it's particularly dilute. You can just follow the chemistry and see it evolve, okay? And what it's telling us is that ethyl propanoate becomes propanoic acid and ethylene, okay? So again, we're getting ethylene from the ethyl ester. And what is it about ethylene? Okay, ethylene is very reactive relative to other species, and hence the difference in reactivity. So ethyl esters will be faster to ignite compared to methyl esters because of this. Okay. Now, so if we look, here's the rate constant. I don't know whether we might have done ab initio calculations at the time. I'm not sure whether we did, but this was the rate constant for this molecular elimination reaction that we included in the mechanism. You see, actually here, the activation energy is quite low in comparison to what we were looking at. For the ethers, the force-centered elimination was about 60 kilocalories per mole. Here, for this six-membered ring transition state, we're down at 50 kilocalories per mole. And it makes sense, really, because it's not a four-centered, it's not a four-membered ring, it's a six-membered ring. Less ring strain. Okay. And actually, if we look at methylbutanoate, and we look at abstraction of one of these hydrogen atoms, let me see if this is, 1, 2, 3, 4, 5, 6. We can have a six-member transition state ring if we rotate around, okay, which could lead to ethylene and this, I don't know what it is, ethanol ester thing, I don't know what it is. But anyway, you can get ethylene and methyl ethanoate or this other species. But it would be ethylene and methyl ethanoate. So it would form this first, but this would isomerize to methyl ethanoate immediately. So you would get ethylene and methyl ethanoate as a product. But we included that rate constant in the mechanism, and it wasn't competitive. Okay? So this wasn't competitive, okay, for the methyl ester, but it was for the ethyl ester. Okay? And so I alluded to this earlier. If we go back a second, I'm going back too far, maybe. But here we have 1, 2, 3. So this is methyl butanoate. But here we have an N-propyl group. Okay? And I said this yesterday, or maybe earlier today, I can't remember. Okay? But when I was talking about hexene, 1, 2, and 3 hexene. And I said, look, this is like N-propyl beside an allyl. And does that behave like propane, or is it faster than propane, whatever? And it didn't behave like propane. Okay? So the question is now, does methylbutanoate behave like propane? So we have a propyl group here beside the ester. And I guess the answer is no. Right? And the answer is no. It doesn't. Okay? But there is some alkane-like structure here that will give you some low-temperature reactivity like an alkane. But the effect of the ester group with that also has to be considered. And you have to include everything in the model to simulate it. But the reactivity seems to come out of the model when you do that. Okay? And so this is what I'm trying to get at here. So here we have propane, and we do see this negative temperature coefficient regime. Here I've actually done a nice job. We have inverse temperature here, and we have temperature on top here. So you can actually see what the temperatures are correspondingly. Okay? And you can see, look, we do get negative temperature coefficient behavior for propane as we go higher in temperature. Okay? So what about methylbutanoate? We don't. Okay? So you might expect, because you've got that propyl group, that you would, but you don't. Okay? So this is phi 1, 10 atmospheres. Okay? And we just see this kind of, there's no reactivity down here, and then reactivity starts at about 800 Kelvin. Below that, we don't see any. Okay? And if we then compare, look, here's methylbutanoate. The stoichiometric ratio is 6.5 times O2 gives CO2 and water. Okay? And we have M-butane would have the same stoichiometric ratio, 6.5 times O2, given us carbon dioxide and water. Okay? So if we compare M-butane and methylbutanoate, what are those reactivities like? Okay? So these are them under similar conditions. Okay? Here's methylbutanoate, here's M-butane. And the reactivity is very different, just because of the characteristics. So in N-butane, if we're at low temperature, low reactivity, we go to chain branching, high reactivity, negative temperature coefficient behavior into high temperature kinetics. We don't have all of that low temperature chemistry happening for methylbutanoate, very different profile. Okay? No overlap, very dissimilar. Okay. Okay. So esters then, these are the only 5 naturally occurring esters that you can make from soybean or rapeseed oil. Okay? You can make methyl palmitate, methyl stearate, methyl oleate, methyl linoleate, and I don't know, I can never differentiate the pronunciation of these two. So anyway, but if you look at this is a C16 N-alkane with an ester functional group, methyl ester. Okay? This is a C18 with a methyl ester. Okay? But look at this one. It has 1 olefin in the... Here we have 2 olefins, and here we have 3 olefins. Okay? So what's going to happen in terms of reactivity, do you think? First of all, what's going to dictate the reactivity of these molecules? Will this functional group dictate it, do you think? Or will this hydrocarbon end dictate? Hydrocarbon end, right? Do you think really the molecule cares about that ester group with all of this hydrocarbon here that can give us all that low temperature reactivity? Not really. Okay? So we're going to get lots of low temperature chemistry here. Okay? Same here. Okay? Same here, here, and here as well. But in these cases, we're getting more and more olefins and olefinic character, which is going to kill us at low temperature because of that R plus O2 shallower well. Okay? Which is not going to help. Okay? And this is exactly what you see. So here's another chart, another slide from Charlie, where he calculated, there were no experiments performed, so he calculated, developed mechanisms for all 5 species, and calculated ignition delay times versus inverse temperature. And here's what's predicted in the calculations. So the C16 and C18 molecules both had very similar reactivities. Okay? But the species then with 1 double bond is quite a bit slower. The one with 2 double bonds is predicted to be even slower, and the one with 3 slower still. Okay? And that's just due to what I said before, the olefinic part. Okay? So it's due to this. You've got the vinylic and allylic. We abstract the allylic. We have, and then we can have superallylic. Okay? I'm reiterating now what I've said before. We can have, here's allylic, but these are superallylic guys. Okay? Because you have the double bond either side. Okay? But there is chemistry that is important for these. Okay? And this slide I like because it shows the link between alkanes, alkenes, and alcohols. Okay? So at low temperatures, you do get olefin plus HO2 through RO2 elimination. You have C5. Okay? So you get that olefin plus HO2. Okay, so let's say you produce the olefin from an alkane, right? That olefin actually can undergo H-atom addition. So this is what we call the Waddington mechanism. So OH adds across the double bond, and actually I think it's about 70% addition or more, maybe 80%. I'm not sure what the ratio is. I can't remember off the top of my head. But it mostly adds to the end carbon, but some adds to the internal carbon atom. Okay? So here it's depicted as adding to the end. Okay? We add to the end, and then we get a radical site here. Okay? That adds to molecular oxygen. Okay? And now the hydrogen atom here migrates to here through a 6-membered elimination. Isomerization, I should say. 1, 2, 3, 4, 5, 6. And that's the Waddington mechanism. It was by a guy called Waddington years ago, or suggested by him, or discovered by him. Okay? And then you produce this aldehyde plus formaldehyde plus OH. And so that's how these olefins are oxidized at low temperatures. So in environments where you have high concentrations of OH, that adds across the double bond, you get that radical, then that radical adds to molecular oxygen, and then you get this propagation. Okay? So now you see, look, what's this? What's that molecule? It's a radical from an alcohol. Okay? So the chemistry of alkanes, alkenes, and alcohols are intrinsically linked. Okay? And so when we're developing mechanisms, we should really, it's something that we haven't done as a community. We sort of look at alcohol and say, okay, we're going to have a mechanism for this alcohol. But that alcohol submechanism, or mechanism, is a submechanism of the corresponding olefin, which is actually a submechanism of the corresponding alkane. And they're all interlinked. Okay? So more and more now in Galway, we're trying to have all of those mechanisms all interlinked and not separate, but all interdependent on one another, and all making sense, one based on the other. Okay, if that, I'm not really, I hope you understand what I'm trying to say. I'm not saying it very well. Okay. Now, so this is in black. In red, then, we have, and this slide is courtesy of Chongwen Zhao. She was a postdoc with me. She's now at Beihang University in Beijing, in China. You also then, though, can have internal isomerization here. This is a 6-membered ring, second addition to O2, and it can go on to low temperature chain branching. That happens, there's a little bit of this. It's only about 20%. Most of this goes through the Waddington mechanism producing this. But this little bit does contribute to the reactivity of olefins at low temperature. Okay? So again, here's another one. This slide you don't have. I added it because Chongwen visited my lab 2 weeks ago, and I decided I'd add a couple of these slides that she had prepared. They're nice. Okay? And so again, you see here you have the addition. You've got some contribution to low temperature chain branching, primarily Waddington mechanism, but there's about 20%, 10 or 20% that goes to branching. And that contributes to reactivity of olefins at lower temperature. Okay? If you didn't have that, isobutene wouldn't show any reactivity here. So if I hope okay. I add it back here. Sorry, here. So you can see, look, isobutene is a little bit more reactive than propene. If you didn't have that bleed, to low temperature chain branching, you wouldn't see any reactivity really down there. Okay, so it's very important. Okay, I don't want to do any more. That's the main message from this slide. I won't go into any more detail on that. Okay. Okay, so this is just showing you then, by adding, so here's predictions of isobutene. If we don't add that low temperature chain branching mechanism and just include the Waddington mechanism, we would get these dashed lines. But by adding that low temperature chain branching mechanism, we get this degree of reactivity at low temperature, which is very significant difference. Okay, and that's just the point of that slide. Okay, and that's it. That's my course finished. I'd like to thank you all for your attention and for your enthusiasm. Keep your enthusiasm, and I hope you have very good careers in whatever you choose to do, be it combustion or whatever else you go on to do, finance, whatever. If you become a banker, remember me. Okay. Best wishes for the future. Okay.